Okay, so I want to spend a few minutes going through examples 4-1 through 4-4, okay? And, the textbook details it out how to go through the solutions, but I want to give you an overview of like the approach, how you would go about solving it, and kind of take a quick look at the solutions, okay? So in the first problem, it says boundary work for a constant volume process. Okay, when we're talking about boundary work, really thinking about it in terms of, you know, the PV diagram, right? So you need to use the PV diagram. And from the information that's given here, it looks like, so what do we have? A rigid tank contains air at this pressure and this temperature. And as a result, heat transfer to surroundings and temperature and pressure inside the tank drops to 65 degrees and 400 kPa. Okay. So one of the things we can recognize from this is what we're talking about is a rigid tank, right? So the volume's not changing, right? So we have a constant volume, right? So we'd expect that, our curve is going to show a constant volume. And what is changing though is the pressure. Okay. So, but as before, we're thinking about this pressure volume or PV diagram, right? So let's see what happens. Well, here's our equation, of course. It's just, from previously what we saw is just pressure and our delta V, okay? And so right off the bat, if you think about it, it's like, what is this really represent? This represents the area under the curve, right? So, going from, state one to state two. Well, if you think about it, it's like when we actually go and draw the curve, you can see that, well, we're starting at state one and we go to state two, right? And we follow this path. But what you recognize right off the bat is there's really no area under this curve, right? So that's going to be zero. And just from definition, right? Delta V, the volume change, since there's no change in volume, this thing is essentially going to be zero, right? And so what they're saying essentially is that there's no boundary work, which is kind of makes sense, right? In this case, is really there's no work being done. It's just in this case, heat is leaving, right? So that's it. That's that one. But the first part of it is to think about, what's the approach? What do you have to do, right? It's like, you can diagram, here's our governing equation associated with it. You can draw the diagram, like I said, the pressure versus volume. You recognize that this is a rigid tank, so the volume's not going to change. So if you know the volume's not going to change, then essentially during that process, you're not going to have there's not going to be any boundary work done, right? Okay. And if we take a look at the second one, we just pull it up, just pulling it up and showing you it, and then thinking about the solution before I actually go and start talking about it, or actually showing the solution. Okay, so just looking at this, we have a piston cylinder, 10 pounds mass of steam at 60 psi. Then you have it at a certain temperature. So now heat's added to the system and it goes to 400 degrees F. Okay. And it says that the piston is not attached to the shaft and its mass is constant. Determine the work done by the steam during the process. Okay. So we have some information given here in terms of it's our initial pressure, right? So we have, this is a pressure volume process, but we have some initial pressure here defined, and no mass is entering and leaving the system. And what you recognize here is that you add heat to it, what's going to happen? You're going to have the volume is going to increase. Okay. And the part here that's important for us to recognize, if it's not attached, its mass is constant, determine the work done by the steam during the process. So one of the things that's going to be constant is the pressure, right? So it's going to have the same pressure throughout because of this. It says its mass is constant. So it's the same force essentially pushing down on it. And the volume is going to change. Okay. So continuing on with this. All right. So a couple of things. Like we noticed that this is it's going to be constant pressure. We assume the atmospheric pressure is constant. Also, it's quasi equilibrium, so it's basically an equilibrium throughout. We can make that assumption. Okay. And we can sketch the system and the PV diagram in process. But we start off with our equation, our governing equation, which is the boundary work between these two states. And one of the things we saw from this is that the pressure is constant, so we can just pull that outside of the integral. And then we have our two states from 1 to 2. So we pull it out, and of course when we do the integration, it's just going to be V2 minus V1. All right? Well, we can also write this in terms of the specific volumes. Okay, so here's our equation for that. And what we recognize is we really don't know anything about these two volumes. Okay, the only thing we can say is that this appears to be it's steam, so it's superheated water vapor, and we have two temperatures, and we have a mass, a total mass of the steam. Okay, so we know this, and we know this, but we just don't know these specific volumes. Okay. Well, since we're given this information in terms of like we know the temperatures of this, and we know the pressure, we can actually use the table to come up with the specific volumes. All right. And the table we'll use is in the textbook, and it's table A-6E. Okay. So you would have to go through and kind of find which table and figure it out. And it's a superheated water vapor table, so that's the one you would look for. Okay. And when we look in that table, and I'll show you that. When you look in the table, and you see, okay, here's the pressure, and here's the temperature, like the boiling point, let's say, or the transition temperature from liquid to vapor. And we look at the pressures. Okay, that's not what we're looking for. 15, 20, 40. Okay, we got 60. 60 is what we want. Okay, so here's 60. 60 at 60 psi. And we're given two temperatures. So we're given we must look at the column first. Okay, so here's our specific volume. All right, that's what we care about. That first column, or the second column, that is. First one is the temperatures. And we go down, and we can pull that right out here. So now we see it at 320 degrees. Here's our specific volume. And then at 400 degrees, here's our other specific volume. Okay? So then we can take those two and go back and substitute into our equation. So if we go back to the problem, and we make those substitutions for the specific volumes. And the only thing is we make sure that, of course, we have the correct units here. Okay. And, we're going to come up with, it's pounds mass. So, when you use that table, at least that one's given in pounds mass for the mass. So you'd have to, cancel out pounds mass here. So you have to make sure that, of course, the mass has the appropriate unit. So you have to make the appropriate conversion. Okay. And of course, the units come out to be, in this case, these two cancel out. So then it's PSIA and these foot cubed, right? So what we would do if we're using the USCS system, we would change it over to BTU. So here's the conversion factor for BTU, right? And that you can look that up. All right, so here's the problem. And if we look at the diagram, here's the diagram, the PV diagram with in this terms. This one's given in terms of specific volumes, but it doesn't matter. It could be given in volumes or specific volumes. This is fine, right? And then the work is just going to be the area underneath this. And the one thing to recognize, of course, when you're talking about like the difference between like if this was volume or specific volume is up here, right? It's this mass, right? So you'd have to multiply, if you multiply this number times each of these, then you come up with the actual volume, okay? That's really the only difference here, right? Okay, so like I said, either way you put this or in terms of volumes, but if you wanted to find the actual work, it's just that constant pressure times that change in volume, right? Which is just, the 10 pounds mass times the difference between these two would give you that. Okay. Okay. The next one's the isothermal compression of an ideal gas. Okay, so we're saying it's an ideal gas, so we can use that ideal gas constant. But isothermal meaning essentially that it's the same temperature, okay, throughout. All right. And our expectation, of course, is that we'll have some changes in terms of, in this case, it says, oh, it's been compressed, so we expect have a change in the pressure also. Okay, so we need to determine the work during the process. Okay, so here's a solution. So it's an isothermal compression process, and we need to determine the work, right? Okay, that's usual. Okay, so we assume it's quasi-equilibrium. Stays about equilibrium throughout, and air can be considered an ideal gas, so we make that assumption also. All right. Okay. So with the assumption that it's isothermal, it's compression, and we have ideal gas, we can make this substitution. Okay. So one of the key points is this isothermal compression of ideal gas is that you make the pressure times volume is going to be constant throughout, okay? And we can actually substitute in for whatever the mass is times that R value of the ideal gas and times the temperature, okay, the initial temperature, or since it's constant temperature, the temperature throughout. And that's all going to be a constant, okay? So this is the substitution we make. And we can also just, taking PV and, saying pressure is equal to this constant, which is this, divided by the volume. Okay, we can also make that substitution, right? Okay. So here's our equation for boundary work. Here's our general equation. And then we make the substitution here for the pressure. So we put in C over V, okay? And then we can pull out C, of course, because it's a constant. And then now you can see the form of our integral, dV divided by V. And since it's our variable integration here is just essentially to the -1 power, we can use it just in this form. It just becomes the natural log of the final volume over the initial volume. Okay. And then, of course, this C on the left-hand side is just going to be the initial pressure times the initial volume, okay? And the reason to do that is, and what we said is, throughout we know that it's constant. This part's constant, okay? So you can either write it like this if you knew the initial volume and pressure, which we do, okay? Or let's say, assuming that you didn't know the initial volume and pressure, and you knew like the final volume and final pressure, or at state 1 and this is state 2, let's say. If you knew only the final volume, or the pressure and the volume at state 2, then you could also have put pressure 2 times volume 2 here, okay? But since we know pressure P1 and V1, we're going to use that. And then when you, a couple of other notes you can, from this, you can get from this. You could have made this substitution. We don't need to because we know the final volume, we know the final pressure. But if you had needed to, you could have said, V2 over V1 essentially is just P1 over P2 since we have this relationship. Okay? All right. So now we have everything we need to go and solve this problem. When we do that, you can actually draw. So here's the curve for pressure volume, and you could just draw this. Here's the process, the path that the process takes from going from 1 to 2. And what we recognize here is that it's a constant temperature. Okay. Well, we can go ahead and just substitute in for the values they're given. And the one last piece here is kilopascals meters cubed is really just a kilojoule. So we want to make that last conversion between the two. And what we recognize is that it's a negative value for boundary work. And the only thing left is this is work done on the system because it's negative. Okay. And that's the end for problem 3. Okay, so for example, 4-4, you have a piston cylinder, and initially at 200 kPa, you have a linear spring just touching this piston, but exerting no force on it. Heat is transferred to the gas, causing piston rise, compress the spring until the volume of the cylinder doubles. Okay, so we're going to double the volume, so we can actually figure out, how much this how much the spring is compressed, right? Okay, so they give you the cross-sectional area. Okay, so we could use that information, right, to figure out what was the distance that this moved, right? So what we have is, this is how much is initially added, so we're going to have double, right? So it's going to be 0.10 meters cubed, okay? Okay, so first part of this, what we can do is actually make a diagram of the system, right? Here's our cross-sectional area, pressure 1, here's our volume 1, right? And we make some assumptions. First part is it's quasi-equilibrium, and the spring is linear, okay, in the range of interest, okay? Then we can go ahead and draw the PV diagram. And essentially we're starting off here, and then here's our final state. So this is like initially, this is final, okay? So at this point, we just don't know where this is yet, right? So we know we have a diagram, something like this. We're going to have some final pressure at that other volume, right? So we have some curve. We just don't know this is at 320 just yet, okay? So first part is we can determine the volume in the final state, which was, of course, the 0.1, right? Which we saw pretty easily. Just initial times 2 gives us the final, right? Now the displacement of the spring, well, it's just x times a is equal to the change in volume, right? Well, we're given the change in volume, and then we're also given the cross-sectional area, so it's easy to figure out what the actual displacement was, right? So it's just the difference between the two. The delta V, which differences between the two volumes, the initial, and the final. Okay, so that just comes out to be 0.2 meters, right? And with that, we can actually figure out what the final pressure is. Okay, so it's just 0.2 times 150 kN per meter. So now we know that force. Now that we know what the force is, we can actually use that to find that pressure, right? The final pressure. And just talking about like in terms of the difference, right? So we have certain force, we have certain areas, so we have a change in 120 kPa from its initial. Okay, so we just add that to our initial pressure, add the 120 to it, and now we have 320 kPa, and that's where we get the second point right here. Okay, all right. Okay. The next part of this, so that gives us our answer for part A, right? 320 kPa. That's the pressure in the final state. Okay. The next thing is part B. Okay, we plot the PV diagram, and then we find the area under the process curve. Okay. So it's just going to be, we have two parts to the area. One is this part 1, and then part 2. Okay. So this one is just, base times height. So 0.05 times 200 is this part. And then the other one, of course, is just half of the area. So it's 1/2 times, 120, which is the vertical. And the horizontal is 0.05. So half of that. right? Okay, so then the total area just becomes this divided by 2. So this is um, so just in terms of like how the author did it, here's our so here's the horizontal component, and what he did is just he basically doubled this and then just chopped it in half. So he said 520 essentially. So taking like this and then from here to here. So 520 would be like from this whole thing. So it'd be like taking the whole thing going all the way up to essentially double this, right? So it'd be 540, right? So 540 be up here, and then cutting it in half essentially will give you this. Okay, so a little bit different way to look at it. Although you could have done it just by what I originally talked about, like, you know, this area plus this area, or doubling it and then cutting it in half. Okay, that's essentially all the author did here. Double the area, then cut it in half, and then just can make the conversion. So now you have 13 kjoules. That's the total work. Okay. All right, and then now the third part, part C, and just going back up. The fraction of this work done against the spring to compress it. Okay, well that is, of course, just this part. Okay, and so we go down here, and it's just going to be the difference between the two. So here is it's 1/2 times P times our volume, right? Here's our change in volume. That's the horizontal component. And it's just half of it, right? So it's just basically the area under that curve, like I was talking about. So it's the area under that triangular portion of the curve, okay? Or you could have done it this way. Here's another option, right? The end result is correct. I'm not sure what this is. It looks like this is an error in the equation, right? It should be 1/2 k times, you know, x 2 squared minus x1 squared. So it looks like we're missing the k over 2 here. And also, so I don't know. But whatever. When you do it that way, when you do it the correct way, 1/2 over do our k over 2 here, and then you do the calculation, you come up with the 3 kjoules. Okay. I didn't even notice that before until I looked at it now in detail. It's like, wait a minute, something's wrong here. Okay, so recognize that. That's how you come up with the 3 kjoules. So either way you've done it's fine. Right? This is like error. This result 3 kjoules correct, but forget about this stuff. And you also need to divide by 2 over here. Okay. The only thing is, it might have been, the author might have been trying to show, you know, 2 over 1 times this and then times that to try to come up with this result, but this is not quite correct. All right.